Welcome to our latest episode of nanoCHAT PuBCluB. This is an Ionic Viper video series in which members of our community share about recent publications. I'm Ann Bentley from Lewis and Clark College, and today I'm joined by Nancy Williams of Scripps and Pincer Colleges, and she's here to discuss her recent publication in organometallics. Welcome, Nancy.
Thank you. Thank
We
you, Ann.
have a link to the publication can be found in the description accompanying this video. And let's chat a bit. Tell me about the
Sure.
research you're presenting in the article.
This is an article about something that didn't work, but it was a proof of concept and the work. We basically said, here's the thing we tried to do. It didn't work the way we expected it to, but all signs are that it's going to work really well in this other system. So what we were really have been interested in since the first time that we really put it clearly to paper was about 2010. And this is the first publication on this, so it's taken us a while, was the idea that you can build a ligand that will make metals better at doing CH oxidative addition of simple molecules like methane.
Mm-hmm.
And on the basis of what we saw in the literature and what we could draw in terms of napkin molecular orbital diagrams, you wanted your ligand to be a weak sigma donor
Mm-hmm.
and a strong pi donor trans to where you were going to bind that CH bond of methane. Long story short, we took many, many years to make this because I'm not an organic chemist. I just play one on TV. And when we finally got it synthesized in 2019, I brought it back to Claremont after my sabbatical. And one of my students, who's one of the authors on this, Maria Liu, was able to put that ligand on platinum. And we were really interested in studying the reactivity of this ligand on platinum.
How did you choose
And
platinum as the first metal?
Well, that's what I've always worked on my whole career is I've been a platinum chemist. I've dabbled a little bit in palladium, but never stayed there long,
Mm-hmm.
which is just really platinum's tricky friend. Um, and so on the basis of some very old calculations from about a decade ago, it seemed like that molecule should CH activate methane. Um, to cut it down to size, I will say we found evidence that it will not CH activate methane. The paper describes some basic chemistry we did to try to take this thing out for a spin. How does it react with acids? How does it react with nucleophiles and electrophiles? And we described that chemistry. We produced a crystal structure of it. But then we went to the computer. I should say that the other student who did a lot of that work, who is also on the paper, is Jacob Kelber, who is now at Penn, and he is working with Karen Goldberg on his PhD. But then we partnered up with Mary Van Vliet, who is a computational chemist, an alum of Harvey Mudd, and has worked with myself and Adam Johnson at various times, who is another member of the Ionic community. And so she helped us computations on these systems. And we were really interested in, are we absolutely at a dead end with platinum? Is this never going to work? And if it's never going to work, we had two questions. One, are there other metals it will work for? And two, are we even barking up the right tree with this ligand? Is it actually better at doing CH activation than a sort of standard garden variety pincer ligand? So here's maybe where I should share a screen. And I'm just going to show you the table of contents graphic. Is this coming through okay for you?
Yes, it looks great.
So what these three images are is they are essentially reaction profiles.
Mm-hmm.
On the left, you have the pincer ligand on a metal bound to a CH sigma bond. And then it goes up over a barrier and breaks that CH sigma bond to make the oxidative addition product where you've broken that CH bond. And the one on the left here is iridium, the one in the middle is rhodium, and the one on the right is platinum. And so what you would want to see is something that has a low barrier and something that is thermodynamically downhill to break a CH bond, right?
Mm-hmm.
If it's uphill, it's not going to break the bond. If it's got a huge barrier, that's also no good to us. You will note that I have no y-axis on here, so I'm depriving you of any numbers. But trust me when I say that actually the barriers to all of these are quite small. They're not, or at least the barriers to the iridium and rhodium cases are quite small. Platinum, you can see, is hopelessly uphill. Now, you may ask, why are there two lines? The solid line on top is sort of a control ligand, the standard NCN pincer. And then the dotted line on the bottom is the molecule that we synthesized, this pi donor, strong pi donor weak sigma donor pincer. So the strong pi donor pincer is definitely much better, but it's still terrible on platinum.
Mm.
You go to rhodium, you can see that the new pincer is much better than the old pincer, but both are thermodynamically uphill. And if you go to iridium, you can see that the new pincer is definitely better than the old pincer. And in the case of the new pincer, it's actually downhill. So if we put this thing on iridium, so saith the computer,
Yeah.
it should break the CH bond of methane. We should be able to observe that compound at low temperature, potentially even make some analogs of that are maybe a little more stable. There are some tricks you can do to make the product a little more stable than you would get with methyl hydride. For example, you can use phenyl hydride, et cetera, et cetera. So that's sort of where we're thinking of going with it next.
Absolutely. That's really exciting. Do you have students recruited to work on the project? I'm getting a little bit of freezing here.
So I don't have current students recruited to work on a project because, yeah, I was getting a little bit of freezing from you too, but I gather that you were asking about students recruited for the project.
True. Yes.
Yes. So, no, because I've been on sabbatical for the last year. And so I've shut down my lab. I also moved my lab because I'm mid-career, and so I'm moving out of the big shiny lab into the smaller, not so shiny lab to make room for a brand new colleague who is joining us on the tenure track, Dr. Anpan, who is going to be joining us in the fall. I mean, he's already joined us. I'm just not there right now. And I am going to be on maternity leave in the spring because we had a baby 11 weeks ago. So yeah, I'm out of the picture for a little while. My plan when I do come back is to start with some computational work. And then with the new year in fall 2025 to start doing some wet chemistry.
Great. Great.
We have a lead on something that's really kind of computationally interesting, which is that it seems to be the case that it doesn't matter what the cis arms of the pincer are, that they can be amines or phosphines, and it doesn't make any difference. And so we're thinking of actually moving to phosphines rather than amines on iridium, because we know the iridium compounds are going to be incredibly sensitive to nitrogen and oxygen anyway. And so we are going to have to do everything under rigorously dry and oxygen-free argon. And so if we're doing that, we may as well have the advantages of phosphorus 31 NMR to characterize these compounds. So it's going to mean some pretty different chemistry for us. We've done a lot of this chemistry on the benchtop or just under a blanket of nitrogen or argon on a Schlenk line. We're going to have to be much more rigorous with this new project.
Great. Are there any co-authors you didn't get to mention that you want to make sure to acknowledge?
Indeed. So there are two.
Effort.
Yeah, there are two. One of them is Adam Johnson, who did the crystal structure for us, which you probably saw in the graphic when I was sharing it. It was at the bottom right corner. The other is Elizabeth Jarvo, who has been my sabbatical host at UC Irvine the last two sabbaticals, and that's where we've synthesized this ligand with great Sturm and Drang. But it's been with the help of a real organic group that understands carbon that we've been able to make the molecule and nail down a good synthesis.
Well, congratulations. I know, working at a PUI, the progress can be, take a lot of dedication over many years with a big team. And it's really great to see this reach publication. Yeah.
Well, and I will say this is not the only thing we were working on, but at the same time, it did take a very long time to bring this one to publication.
Yeah, yeah. Well, it must be great to see it.
It really
and for
is.
your students too. It's just fantastic. Yeah, great. Well, thanks to everyone for watching our nanoCHAT. And if you have any questions, we have a very active Discord server through the Ionic Viper website, and we'd be happy to continue the chat there. And if anyone is interested in being a guest on a future nanoCHAT, reach out to the Ionic leadership team. And thanks again to Nancy for taking time out of maternity leave to come talk about this really exciting publication. Congratulations again.
Well, thank you. And thanks so much for taking the time yourself, Anne. It was good to see you.
Yeah, nice to see you. All right, take care.